Good afternoon, everybody in my physics classes. I just would like to organise myself a little wee pretend computer mouse pointer here. I'd like to look at the key ideas in the book for rotational kinetic energy. Key ideas from my point of view. And then look at the swivel chair, which is an interesting situation. By the way, this video would be useful for my students. I'm only making it a few minutes before your lesson. I've been trying to make these PowerPoints first. And then this will be up there for Mr. Kumar's class, who's doing things in a slightly different order from us. And leave everyone with a question. And when the question comes through and you figure out the answer, please email me. I'd like to hear what you come up with. So the key ideas from the book are found on page 114, and there it is. If you haven't got your book in front of you, that's fine. You can pause the video. And they've just basically summarized some things here. I've pulled some stuff out of down here. From my point of view, if we do the straight correlation, the linear kinetic energy is half times the linear inertia mass times the linear velocity squared. And so therefore rotationally, the rotational kinetic energy is the correlation. M goes to I and V goes to omega. And rolling objects have both, and they are linked because omega is V upon R, or V equals R omega. Things that go running past orbiting objects like the moon, or a runner going past a person. If any object going past another object has angular momentum, L equals mvr. You can use this if you imagine somebody running up and then jumping onto a roundabout. They would have tangential angular momentum. So therefore, orbiting objects include people running if you've got a person off to one side or a point off to one side. Here's an example. I'd like to go back to the spinning chair that I did in the classroom, and also I've got a YouTube clip of that which I might put in the Google Classroom too. So I spin on a swivel chair, two big heavy masses, as you can get my heavy masses in my picture here, pull them in and spin faster. So little example here, I spin with an initial angular velocity of 2 radians per second. I have a moment of inertia, that's the rotational inertia of 2.7 kg square meters. Then I pull the weights in, so the new moment of inertia is only 0.6, squeeze up small. Find the following. I'd like you to find my initial rotational kinetic energy, my new rotational velocity, my new rotational kinetic energy, and the size of the change of energy. And when you have a change of energy, work is done. We need to talk about work being done here. So my initial rotational kinetic energy. By the way, at any stage, I would like you to pause this video so you can do the calculation yourself. I'm about to do the initial rotational kinetic energy, and you can pause this and work it out for yourself by going back to get the numbers. That's the formula we just put down. Put the numbers in, half times 2.7, that's initial angular momentum, angular rotational inertia times omega squared, and we get 5.4. That's cool. Joules, that is. Not very many joules, but that's okay. My new rotational velocity will go up. So we start with L equals I omega, and we find the initial angular momentum is also 5.4. It's a coincidence because I made the numbers too nice. It's this is times 2, another one is times half of 2 squared, so therefore it's the same thing. Please don't pay any put any value on the numbers being the same there. So I omega is L, swap sides, and then we start off with L equals I omega, swap sides, I omega is L. We want omega by itself, so we divide both sides by I. And then we get the numbers in, 5.4 divided by 0.6, and we get 9 radians per second, which is whooping around 3 revs in a second. Yeah, that would be about right. My new rotational kinetic energy. Again, feel free to pause this video and do the calc yourself. EK is R is a half I omega squared, a half times 0.6 times 9 squared. So my new kinetic energy is 24.3 joules. Now, your mission is to find the change of the amount, change in the amount of energy. But to change the amount of energy, work must be done. What work was done? Well, It's gone up from 5.4 to 24.3. This is an increase of 18.9 joules, or 350%. So something has done work on the system to increase the rotational kinetic energy. Where did that energy come from? What caused that rotational kinetic energy to increase? In this case, the rotational kinetic energy did not do work. Work was done on it by something. I'm not going to answer that question in this video. I'd like you to send me an email when you figured it out. Cheers, everybody.